Hello, good afternoon, all. I hope you can see me and my screen. Thank you for joining this first session. That is a Tech Brew session. And today we will be discussing about the topic, which is reduce design rework drastically. Right. So let me minimize this. Yeah. So, like any rework, design rework is also very critical from different aspect of a product development situation or any business for that matter. And when we analyze this rework or the reasons of rework, there might be many reasons which are not technical in nature. But there are some reasons which I think are quite technical and which are in control of of us, right? So the first one is under design. So under design, as you know, is can be because of many aspects. I mean, on account of many aspects, it can be on stress, it can be on the displacement, stiffness, anything. But whatever might be the reason, under design can have dramatic or drastic effect on if it goes unnoticed. However, most of the time it will be detected in CAE section of your company, and then that might again the design might again come back to the CAD team, and which will cause the time delay. On the other hand side, over design is not that critical on not that sometimes it go unnoticed because of many reasons, and that also affect us in the project side, because that will add up our cost of material as well as other operational cost, right? And again, it will, if it get noticed, that will again create a loop of redesigning. On the other next one is integration issue, where especially when the projects are complicated or when mechanisms are involved, there might be some integration challenge. Although the design is well designed, but then there might be integration challenge or interference or unnecessary clearances, right? So those things create problems in the integration stage, and that might again come back and create the redesign or rework of the design loop. And then another one, which is also very critical one, is manufacturing issue, which might get detected during the supplier or the prototype stage, right? It can be detected either at the supplier end or the prototype end. And again, it can come back to the design stage and it create the design rework loop, right? So to see or to address this issue, how can we address this issue through our tools, right? So for that purpose, what I am going to talk today is the tool or the platform of Altair, which is called Inspire, which is our simulation driven design platform. And we will take example to show how these different causes of design rework can be addressed by using a different part of this platform. Now, for those who don't know Inspire, this is a very easy to use yet accurate platform which has a unique capability to interact with multiple of our proven solvers, like MBD solvers like motion solve. It can be interacted or can be accessed. It can access the solver like OptiStruct. It can also access our different set of manufacturing solver like casting solver or injection molding solver and so on. And it also can access our newly acquired solver, that is SimSolid. And for those who don't know SimSolid, it is a structural simulation solver that operates directly on original unsimplified CAD geometry and don't require a mesh to be created. And also it gives very accurate result in a much faster time span, right? So all these things together, we'll see how to take and how to solve those rework issue, design rework issue, by taking this example of a hydraulic tailgate lift. So this is the attachment of mostly the pickup truck, where heavy component can be lifted in the pickup truck with easily, because this platform kind of moves with hydraulic actuation, right? It also acts as a flap at the to close the this pickup truck's end. So without further ado, so let's go to the tool and show how these things really work. Right. So we'll start with the CAD of that CAD of a version of that hydraulic lift, and then what we'll do is in the first stage we'll use the SimSolid solver, right? We'll use the solver as SimSolid over here, and then what we'll do is we'll try to apply the necessary loading condition. So in this case, we are going to apply 2.5 ton load, and we are going to apply the boundary condition. Basically, this is where we are fixing this structure, and this is the part of your car structure, right? And we also have to make sure that our gravity direction is in proper manner, and then we'll ensure that our connections are created all right. So here I am trying to create little more detailed connection. I know this is not I'm not going very deep into this each of the tool. The reason for that being is that there will be subsequent sessions where each of the tool will be explained in a greater detail, right? So now once this much is done, we can go ahead and run our first iteration of the solution simulation to understand the whether it is under design or it is over design or how is the stage, right? And as I said, it is using SimSolid as a solver, and SimSolid has its own unique capabilities of not being created mesh and also the speed, right? And that you can see it over here. This is a reasonably big platform, and you can see that I am getting a kind of a displacement or deformation in the range of say 23 mm. Anything below, beyond 21 is not considered a very good design. So in that aspect, of course, that number can be debated. For this particular application, I am fixing that 21. So in that, with that logic, this goes into under design, right? So now the question is, if there is under design, how to tackle this under design, right? So to tackle this under design, there can be many things which can be changed in the structure. But for this particular use case, what we are changing is this: we are focusing on these two arms, right? And if I have to redesign or modify the design of these arms, what are the parameters I can really redesign? So there are, what I can see is that if I have to really keep this shape and I have to play with the parameter, I will probably play, this is probably my one parameter, what I will probably redesign. That means the width or depth of that arm. This could be my second parameter. So that means this dimension could be my second parameter. This could be my third parameter. So that means this internal cutouts depth. This could be my third parameter, right? And I can also play with other two sides of this cutout. So that means this would be my fourth parameter, right? So this is my fourth parameter, and this could be my fifth parameter, right? So I'm just creating this five parameter to play with the different dimension of this arm. And I will simply copy those parameters to other side of the arm as well, so that all of them kind of come in sync. So what I'll do is I'll keep this as a parameter 1 and this as my parameter 2. So if you see that I have just not creating another new parameter, rather I'm just using the same parameter and then giving this as another parameter over here. Just copying that parameter over here. So this dimension. And then I will similarly use this dimension to make it like fourth parameter. And then this one is my fifth parameter, right? So this is my fifth parameter. Oops. This is my fifth parameter, right? So now what will happen is I have all these parameters defined for this particular arm. And now I can play with this parameter. So for example, now I want to change the depth of this particular arm by say another 15 millimeter. So if I do that, if you observe, I don't know whether you could observe or not. Let me do it again. So I can change it. And similarly, I can play with any of those parameters, right? And then I can quickly go and check my displacement, which I'm targeting. So I can go and rerun this model again. And it will do the keep everything else same, and we'll try to assess the structural, mostly the displacement over here. and see how my change on this parameter kind of plays role in the target value. That is our overall displacement of the complete structure, right? So yeah, so it is done. Now I can check, and you see that it indeed helped me. So from 23.5, it goes to kind of 21.3-ish, right? So it is coming from under design towards maybe the better design. But you might have observed that this is not the most systematic way to do this kind of thing. Rather, what if I would like to play all possible combination of these parameters in a more systematic way, right? And that's exactly what we can do through our design explorer available within Inspire. Of course, it has another version available in other tool like HyperWorks as well, which we will discuss maybe next session. But here what we're doing is we are now accessing all those parameters, whatever we have created, and we are doing a optimization study with these variables. So now I'm telling that all these variables, all these parameters can range from say 0 to 25, right? 0, sorry, this one. So we'll change this from 0 to 25, 0 to 25, 0 to 25, and so on, right? And once I'm done that, what I'll do is I'll take the responses. I will take two responses. One is displacement, the global maximum displacement rather, and I'll take another responses that will be my mass, right? So I'll take both of these responses, and I'll set up my goals. Like my objective would be to reduce my mass, of course. So I want to reduce the minimize mass, and I would also like to constrain my displacement, say below 21 mm, right? So that's my target. And then I can run all the iteration. Here it is telling 50, and I can simultaneously run multiple iteration as well based on my server's PC's capacity. And I can then run. I'm not running. Of course, that will not make sense because it will take maybe 5-6 minutes. And what I'll do is I'll show you how it will look like when it runs. So you see that there will be, here in this case, I have done 10 run. And I see one iteration where I could achieve that close to 21. And if you see the initial run, that is like it has around displacement of 21.74, and it has come to 21.03. And if I load this run over here, you can understand that result in a much more detail like we did for other runs. And then we can also compare this. So I can say, okay, compare it with the normal run, nominal run, and you can understand that how these things are varying. So you'll see that it is 3% lower than the displacement of our initial best by expanding the thickness. And of course, with the cost that it will have little more extra mass as well, right? So you'll see that mass has been added over here. But this is by far the most, another approach where if you want to do parametrically modify your design to make it properly designed, then you can, of course, take help of this design explorer, right? What if I want to explore more? So that means I have this study you have done. If you remember, we have done it in our SimSolid solver, and I want to do further detailed study in SimSolid. Can I do that? Answer is yes. So all those things what has been set up in Inspire using SimSolid can be taken to a native SimSolid solver, and you see that everything has been set up. And you can then do further analysis, advanced analysis, such as your nonlinear study or say thermal study or say transient or vibration studies or say fatigue studies and so on. You can also enrich additional connections. So for example, I want to enrich this load tray with say additional welding. So I can do that very easily. So I can go ahead over here and I can say that I want to connect it with say, with my welding, right? And with that, I can do further study over here. So I can go ahead over here and I can check how my result is getting changed over here after adding the additional welding connection. Of course, I would not expect huge change in the result because of obvious reason, but it opens up a door to take the setup in Inspire and do additional study without putting extra effort and setting up over here. Of course, you can do setup over here as well. So that way, it might be more meaningful if you do it, say, other studies, for example, consequent study or say combined study, right? So you'll see that it has not changed. But what you can do is, because you have changed now the welding connection, you can also get additional response like welding reaction forces, which might be useful for it, right? I'll stop with SimSolid at this point because there are subsequent session detailed on SimSolid, subsequent coffee tech brew session. So now what I want to show is that what are other options you have as far as the this modifying this design in to make it like properly designed. So one more options you have is that using a optimization method, not like parametric optimization, but using our solver OptiStruct to do a topology optimization method. And to do that, what I can do is I can isolate this geometry, and then what I'll do is I will simply remove these cutouts from here. So I'll find this cutout and I'll remove it, right? And then I'll declare this as my design space. And with the same loading condition, what I'll do is I'll go to my structure, and instead of running analysis, I'll do a optimization now. And here I can give a topology as my type of optimization. And I want to give the percentage of material removal. Okay, so here I'm saying that I'm removing 70% of my material. You have other options as well. For example, you can give factor of safety, frequencies, or say certain frequencies to be achieved or minimum thickness to be achieved, and so on, right? And you will run it. So once you run this, what you will get is this optimized shape, which will help you to visualize your design, which might looks very unobvious, right? So this is a design which kind of you are challenging your basic architecture of your existing design itself, and you see that this is what you got. So this is the most optimum one through topology optimization. Now, I also talked about how to check the fitment issue, right? Integration issue. So what will happen if there are some integration challenge, right? So to do that, to handle those kind of situation, what you can do is I will just bring back my old model. So here I have started. And what I'll do is we can take help of our MBD solver, so which is motion solve, which is a known solver for industry for long. And here what I'll do is I will set up this problem. It's again very easy. So all I have to do is I'll make sure that I have right group in place, right? So this is my groups, and then I'll create the joints. So you'll see that it automatically create the joints where it is required, and these joints can be customizable. It's not that you have to go with the same joint what has been suggested. And once that joint is done, you can define your actuators. So these are the actuators. So there are 4 actuators in this assembly. This is another actuator. So this is wrong one. I have to delete this. And then you can define the properties of the actuators very easily. So for example, I'm locking these 2 external actuators, and I am also making sure my gravity direction is correct, and I am adding the mass what it should withstand like before. So that is 2500 kg, and that probably all. Okay, apart from this, we have to ground this particular member. And then you can go ahead and run this simulation, but this time through MBD, right? So you'll run it. So it will give you the animation or the simulation. And what all information you can extract after this. So the most first and foremost information what you can get out of the simulation is the loads coming on different load points or different hard points of this system, which is very, very critical if you are really want to go deeper in any of the component. For example, say ARM, you can very easily extract this load and output this load. You can also extract the forces which stand or forces required by each of the actuator, and that will be also useful to design or size your actuator. Most importantly, what you can do is you can understand the fitment issue. So for example, if you see the rod over here or the bracket over here which is suspended, which is protruded, and the platform over here, if you see from any particular view, it will give you kind of not so clear picture whether it is going to interfere or not. Let me change the color so that you can understand it better. So if I redo it again, so if you see this in this view, you will not have clear picture that whether this particular bracket and the platform is going to interfere, or if it is not, what is the clearance. It looks like this is going to interfere from this view, but however, if you see from this view, looks like there are huge gap, right? So you as a designer might not be very sure from a static position that what might be the distance and different snapshot of this system, and that's where this tool can help you. So what I have to do is you have to take what is we call part envelope, and what it will do is it will automatically give you the different instances of a component for different position of its travel, right? So it is trying to create that geometry for you. So you see it now. So now you see that it is from this position to this position, and none of the position are actually interfering over here, right? Although from this angle it looks like it is kind of hit, but that is not the case. So this, and you can then export it as a CAD, and you can do your DMU study and all those things very, very easily, right? So that's how you can do the interference study. There are many more, like any other tool, whatever I explained, I just explaining it in little high level, I know, because that's what the purpose of this first session. Each of the topic will be explained in a much deeper, greater detail by respective expert in subsequent sessions. So I will urge you to stay tuned. So with that, I'll go back to my presentation, and I'll probably show you few of the case studies, right? So the first one being the right sizing optimization or right sizing study by one of our customer who used this simulation driven design approach to rightly size their member in the panel B or inner panel of their bonnet. And that's what you can see in the right hand side of your screen, where their existing design had a cross kind of member, which was kind of eliminated because of this study's finding of this study. And it also brought many other benefit which has been mentioned over here. And the most important benefit is that achieving the right sizing, or rather not allowing the defect to go beyond designer's computer, right? As you know from your Lean Six Sigma and other philosophies, more you allow your defect to travel, more cost you have to bear, right? So the whole idea of this simulation driven design is to restrict the design or find the design from all angle right in the designer's desktop, right? This is another example where it is little bit offbeat. You might not, if you are an automotive designer, you might not handle this kind of problems, but the people who are designing the plants, they need something called gripper, which holds the car from one station to another station. And those grippers are held by a robot whose size is limited. So the cars are getting heavier and heavier, and the robot has limited capacity. So gripper has to be optimized, or it has to right sized. Here over design kind of comes into picture. And you see that through the methodology, the existing design was redesigned in a much more leaner and slimmer way, but it is much more structurally efficient. So you see from there that you could get around 20% reduction in the mass without compromising really the stiffness or the stress. This is another example of right sizing, or rather not allowing the defect or discovering the defect in the design stage, and this is using our technology called SimSolid, which is using to evaluate a shock tower in different scale. So you see that it is being evaluated at a component scale here. It has been evaluated at a kind of sub-assembly scale here, and it has been evaluated at a test rig scale over here. And that's the beauty of SimSolid, because that solver is so much of high capacity that you can bring as much as you can as far as CAD is allowed, and you can very precisely kind of quantify your problems upfront during your design stage.